High to low, look out below.
Eh.
It sounds almost like a nursery rhyme, doesn't it? Something you might, hear kids chanting.
It really does. It's one of the first mantras drilled into your head in a flight school.
Right up there with aviate, navigate, communicate.
Exactly. But the scary part isn't learning it, it's how easily it can slip your mind when you're tired. It's pitch black out, and the weather is just miserable.
Welcome back to the deep dive. Today we are bundling up and heading into the freezing cold. We've been unpacking a fascinating stack of documents on cold temperature non-precision approaches. Specifically, we're looking at how to manage the Airbus A320 when the mercury really drops, and the stakes in the source material we're covering today are just incredibly high.
They are, because the fundamental premise we're dealing with today isn't just about being uncomfortable, it's terrifyingly simple. When the air gets cold enough, your altimeter,
The one instrument you trust with your life.
that's the one. It is essentially lying to you.
That's the part that really jumped out at me. You're sitting there looking at the dial, and it says 2,000 feet. You feel safe. You think you have plenty of buffer.
But in reality, outside that window, you might be significantly lower.
And if you don't account for that,
If you don't do the math, you are flying a perfectly functioning airplane into the terrain. This is the absolute core of controlled flight into terrain, or CFIT, in winter operations.
a chilling thought.
Oh.
So here's our mission for this deep dive. We're going to unpack the physics of why the atmosphere shrinks and tricks our instruments.
Then the specific Airbus guidance modes.
Yes, because the documents make it clear that not all magenta lines are created equal. And then we'll walk through the operational how-to, so, we don't end up as a case study.
We'll cover the science, the buttons you push in the A320, and the really dangerous traps like that famous geometric paradox that have caught out even experienced crews.
Okay, let's start with the science. I want to understand the why before we get to the how. Why does the cold make a precision instrument like an altimeter a liar?
Well, they are precision instruments, but they're calibrated to a specific model of the world.
The International Standard Atmosphere, ISA.
Right. And in that perfect theoretical world, the temperature at sea level is 15 degrees Celsius, and pressure changes at a very predictable rate.
So the altimeter is just programmed to expect the air to behave a certain way.
It's expecting a standard day. It measures pressure and translates that into altitude. But here's the problem. Air is a gas. And basic physics tells us when you cool a gas,
It contracts.
it contracts. The source material used this analogy of a column of air.
I found that really helpful to visualize.
It's the best way. Imagine a column of air over the airport. On a hot day, it expands, gets taller, but in the winter, when it's, say, minus 20 degrees Celsius, that air gets denser.
The molecules huddle together.
And the whole column compresses. It physically shrinks towards the Earth.
So the pressure levels,
Yeah.
they literally move.
The pressure levels physically slump closer to the ground. But your altimeter doesn't know that. It just feels the pressure and says, oh, based on the standard model, this pressure means you're at 2,000 feet.
But because the whole atmosphere has slumped down, you are physically lower.
Which brings us right back to that mantra.
High to low, look out below.
That's it. It's not a mechanical failure. The instrument is working perfectly. It's the atmosphere that's failing to be standard.
That distinction is key. Okay, let's transport ourselves into the cockpit of an A320. It's minus 20 outside. Usually, modern pilots love the automation. We love following the magenta brick.
The magenta brick, yes, the vertical deviation indicator. In the Airbus, the gold standard for a non-precision approach is a mode called final APP.
Fully managed guidance.
The plane just flies itself down the profile like it's on rails.
But I'm sensing a massive but coming here regarding cold weather.
It is a massive but. See, final APP uses a barometric vertical profile. The computer sees a waypoint that says, cross this point at 3,000 feet, and it aims for 3,000 feet on the
On the barometric altimeter.
which we just established is reading high.
Oh, wow. So if the altimeter says 3,000 feet, but you're actually at 2,700.
The magenta brick path itself is physically lower and shallower than the chart intends. The automation will happily fly you into the ground while telling you you're perfectly on profile.
That is incredibly deceptive. Does Airbus actually put a hard limit on this?
They do. It's usually on the approach chart or in airline SOPs, but typically if the OAT is below, say, minus 15 or minus 25 Celsius, you are prohibited from using final APP.
You just can't trust it.
The error becomes too significant to ignore.
So if it's minus 30 in Edmonton And we can't use final APP. Are we back to hand flying it like it's 1970?
Well, if you're flying a newer jet, you might have the hero mode. It's
Oh.
called FMS landing system.
The documents were raving about this. What makes FLS the hero?
The magic of FLS is that it creates a virtual beam. It mimics an ILS signal, but it builds it mathematically. And the crucial part is that FLS automatically compensates for the temperature.
How does it do that?
It uses the geometric position of the runway and your distance. It doesn't just rely on pressure. You tell the computer the temperature, and it mathematically creates a geometric line in space that doesn't shrink just because the air did.
That sounds like a dream. The
Yeah.
computer does the math for you.
It is. It lets you fly a managed mode, even in temperatures where final APP is, well, illegal. It's a huge safety enhancement.
Not every plane has it, right?
Correct. A lot of older A320 fleets don't. It's a customer option.
So if we don't have the hero mode, and it's too cold for the magenta gruck, what is left?
Now you're in what I call the Wild West of selected guidance. You have to use a mode called NAVFPA.
FPA, flight path angle.
Right. With FPA, you are just telling the plane to fly a specific angle. You dial it in yourself. You say, descend at minus 3.0 degrees.
And the plane just puts its nose down and holds that angle.
It holds that angle relative to the air map.
Why do you call it the Wild West? It sounds stable enough.
Because it's dumb automation. It provides zero terrain clearance protection. The plane doesn't know where the ground is. It just knows hold minus 3 degrees.
So if you set the wrong angle, or start at the wrong spot,
It will fly that angle right into a mountain without a single complaint.
so the workload just skyrocketed. You went from monitor the computer to don't let the computer kill us.
Exactly. It's a huge shift in mental gears.
All right, let's get into the nitty-gritty, the operational how-to. When do I actually have to start doing math in the cockpit?
The trigger is usually 0 degrees Celsius. Or you look at the approach chart, sometimes there's a little snowflake icon with the temperature next to it.
And we aren't just guessing, right? We're not just adding a couple hundred feet for good measure.
Absolutely not. Never guess. The Bible is the ICAO cold temperature error table. It's in the quick reference handbook.
Okay, so I open the book. What am I looking for?
You're looking for the height of the fix above the altimeter setting source, so usually the airport. If the airport is at sea level and your fix is at 5,000 feet, you look at the 5,000-foot column and the temperature row.
And the table gives you a number.
Maybe 480 feet. So your 5,000-foot clearance becomes 5,480. That is the altitude you must fly to ensure you are actually at 5,000 feet true altitude.
Now, the documents broke this down into segments, which I found really interesting. Let's talk about segment 1.
Segment 1 is the initial and intermediate approach, the IAF and the FAF. You must correct these. But here's the crucial point. You must advise air traffic control.
Why do I have to tell ATC?
Separation. Think about it. ATC might have another plane crossing 1,000 feet above you if you suddenly decide to fly 500 feet higher than charted.
Ah, that makes sense. You're eating into their buffer. So what do you say?
Standard phraseology would be something like, request 5,000 feet for cold temperature operations. You get their blessing.
Got it. Okay, what about the final segment?
This is the descent to the runway, specifically the minimum descent altitude, or MDA. You absolutely must correct this. But, and this surprises people, you generally don't report this correction to ATC.
Really? That seems counterintuitive.
It's about airspace protection. Once you are inside that final segment, you're cleared for the approach. The controller protects that whole block of airspace for you.
So you own that space.
Right. Whether your personal minimums are 400 feet or 460 feet doesn't really impact their separation plan.
I see. And then the missed approach.
You correct the missed approach, holding altitude, and because you're going back up into traffic, you advise ATC again.
Okay, so we've done the math. How do we get these new numbers into the flight computer? Surely the A320 helps us out.
In a modern A320, we have a function called tempcompmt in the MCDU. It's pretty slick. You enter the temperature, and it adjusts the waypoint constraints automatically.
That sounds incredibly helpful.
It is, but here is the gotcha, and I cannot stress this enough. The system corrects the waypoints in the flight plan, like the FAF. But on most software versions, it does not correct the MDA or DA automatically.
Wait, really? The most critical number, the don't crash altitude, isn't updated by the tempcomp button.
Correct. It is a massive design trap. The pilot has to manually calculate the new MDA and enter that specific value into the Bayero field.
Wow.
If you assume the computer did it all, your minimums will be set too low.
That feels like a huge hole in the logic. I fixed everything for you, except the last 200 feet.
It's a classic automation pitfall, expectation bias.
Speaking of traps, let's step into the instructor's corner. The source material spent a lot of time on the Air Canada 624 scenario, the crash in Halifax.
A tragic example. They were using that selected guidance mode we talked about, FPA. They did the right thing initially. They corrected the final approach pitch altitude.
So they started higher than normal. Sounds safe.
Yes. But then, to make the math work, they steepened their descent angle. The standard was maybe -3 degrees. They dialed in something like -3.5.
I can see the logic. Start higher, you need a steeper slide to hit the same spot. It's just triangles.
It sounds logical, but it creates a geometric paradox. Remember, the temperature error depends on your height above the ground.
Right. It's bigger the higher you are.
Exactly. At 3,000 feet, the error is large. But as you get closer to the ground, the error shrinks to almost zero.
I see where this is going. The buffer isn't constant.
It decreases as you descend. But the pilot has set a constant steep angle of -3.5 degrees. So initially, they're on path. But as they get lower, that steep angle causes them to slice right through the correct path and end up below it.
So by holding that angle, they effectively dive-bombed the runway threshold.
Effectively, yes. They hit the approach lights and an antenna array short of the runway.
Terrifying. So what is the fix? If you can't just steepen the angle, what do you do?
You have to disconnect angle from safety. When you're using FPA in the cold, the only source of truth is the distance versus altitude table on the chart.
The little table that says at 4 miles, be at 1,200 feet.
That one. You have to watch it like a hawk. At 5 miles, check altitude. At 4 miles, check altitude. If you are lower than the corrected value on that table, you must level off.
You can't just set it and forget it.
Not at all.
That brings up another message pilots might see. Too steep path.
Yeah, the MCDU might yell at you. In cold weather, it's a warning. But oddly, you can see this in hot weather, too.
Hot weather. Why?
Well, think about the reverse. In hot weather, the air expands. Your true altitude is higher than indicated. So to get down to the runway, the plane calculates it needs to dive steeply.
So it's protecting you from a dive bomb in both directions.
Basically, yes.
One more trap from the notes, the MDA buffer. What's that about?
This is for when you're flying these approaches manually. If you decide to go around exactly at the minimums, the plane dips a little bit while the engines spool up.
Inertia. It sinks before it climbs.
Right. It's safer to add a buffer, say, plus 50 feet to your corrected MDA. That way, if you execute a go-around, you don't accidentally bust the hard floor you just calculated.
A great practical tip. Okay, we've landed safely. We're taxiing to the gate. We can relax now, right?
Not quite. The notes had some surprising ground details. First, flaps.
What about them?
If you land in slush or snow, the standard advice is do not retract the flaps and slats.
Leave them hanging out.
Leave them out until the ground crew checks them. If you retract them, you might crush the mechanism with ice, or worse, retract wet slush into the wing, which then freezes solid.
And then you're grounded.
An expensive mistake. And here's another one for the engines. If you taxi in icing conditions for a long time, ice can build up on the fan blades.
Just from the suction.
Yes.
Yeah.
So before takeoff, you might have to do a static run-up. Hold the brakes and rev the engines to about 70% in one for 30 seconds.
Just to shake the ice off.
Creates centrifugal force, sheds the ice. You don't want to take off with unbalanced fan blades.
Fascinating. It really is a battle against the elements from start to finish.
Winter flying is unforgiving.
So, let's bring this in for landing. If you had to distill this down to a few golden rules, what would they be?
I'd bring it back to the Airbus golden rules. Fly, navigate, communicate, but with a cold weather twist.
Okay, break it down.
Fly, use the right automation. If you have FLS, use it. If you're using FPA, acknowledge you're in a high workload environment. Don't be passive.
And navigate.
Navigate means knowing your true vertical position. Cross-check the distance altitude table. The chart is the truth. The altimeter is an estimate.
And finally, communicate.
Tell ATC what you are doing. Don't surprise the controller.
I love that. It brings us back to that provocative thought. We spend our careers learning to trust the instruments.
It is, but in the cold, the most dangerous thing in the cockpit might be the pilot who blindly trusts the green bird.
The instrument is telling you a pressure altitude, not a geometric truth.
If you don't cross-check the chart, you are effectively flying blind.
A sobering reminder to check your charts, check the thermometer, and never take automation for granted. Thank you for guiding us through the freeze today.
My pleasure. Stay warm out there.
And that's it for this deep dive. Thanks for listening, and we'll catch you on the next one. Stay safe.